we're class 30 today. We're going to begin rational functions and their graphs. We haven't looked at rational functions yet. We're going to spend 2 days on this. So anytime we spend 2 days on a topic, it's kind of a meaty topic. And then we're going to spend, just before Thanksgiving, we'll start our exponential functions. Again, 2 days on that, and begin logarithmic functions. We're going to have a take-home quiz today that will be due on Wednesday. Same directions as usual. Any resources is fine except for another person. Again, I will probably mention this every Monday. On your schedule, it says that our final exam is the 21st. It's really the 18th. It's Friday the 18th at 8 a.m. So if you haven't made that change yet, or made that note for yourself, or put it in your online or iPhone calendar or your Samsung Sun calendar, please make that change, okay? So let's take a look at these preview activities. And this is the first time you've seen a graph of a rational function, and it looks a little different than our polynomial functions, because all of our polynomial functions, you could start on the left-hand side and trace them with your pencil in their nice smooth curves. You never have to take your pencil off the paper to draw the or to represent the function. Whereas here, if we started on the left-hand side and went towards 1, notice we literally have to pick a pen or a pencil off the paper to then go up here and come down through here. So this has some features that we haven't seen before. It has these sort of kind of gaps that we haven't seen along a vertical line here. Also notice it has this little hole right here at x equals 2, 1. So at 2, 1, the function is not defined. It has a hole. So the function is not defined at x equals 2. So x cannot be 2. It has no value. The function has no value. And then the other thing that we notice is that x cannot equal 1. Because as you listen to this language, it's new language. As you approach 1 from the left-hand side, notice my finger's coming in from the left-hand side, the value of my function represented by the line is going towards negative infinity. As you approach 1 from the right-hand side, the value of my function is blowing up, getting bigger and bigger without bound. So now we're talking about coming in from 2 directions towards one particular value of x. And noticing that this dotted vertical line, which we call a vertical asymptote, this dotted vertical line, which has this equation, x equals 1, is what we call a vertical asymptote. And that was given to you in your preview exercise. So a vertical asymptote is a vertical line of a graph that, on a graph that your graph approaches, but it never touches or crosses. You can never touch across a vertical asymptote. It's untouchable. And that's because your function is undefined. The value of 1 is not in the domain of your function. So maybe some of you already can think of a function that has the value x equals 1 not in the domain. What might the denominator look like if 1 is not part of the domain? What might the denominator look like if 1 is not in the domain? X minus 1. So that's, there's other possibilities around that, but if you put a 1 in there, then your denominator is 0. Okay. So this is the definition of a vertical asymptote. You should make sure you highlight that in your notes, because we're going to be talking about these quite a bit. And the other idea, which is a little different, is this idea of a horizontal asymptote. Little different idea. So let's try to take these a little slowly now. So the vertical asymptote of a graph is a vertical line that our graph approaches but never touches or crosses. Okay, does not touch, and I'm going to put here or cross. Okay, it's forbidden. Okay, it's like a barrier. Okay, if you never cross or touch that line. However, a horizontal asymptote is a little different idea. It's a horizontal line on your graph that your graph approaches. Think of your end behavior. As x gets really, really large and really, really small, as x moves towards positive infinity and as x moves towards negative infinity, the graph gets really, really close, but it doesn't touch it. It can cross it. Sometimes it will cross your horizontal asymptote. It's allowed. It's not like a value that makes your denominator zero, but it tends to just be a value that your function approaches. So if we were looking at our y values along here, what might this y value be right here for 3? If we just estimated, what might the y value be? Half? What about when I get down to 4? Fourth? What about at 5? Fifth? So what's happening to the value of my function? I'm going from a half to a fourth to a fifth. What's it getting really close to as this line extends further and further to the right? What value of y? 0, right? So as this graph gets further and further to the right, my value of my function, my y value, is getting smaller and smaller and smaller and smaller and smaller. It's getting very close to 0. And similarly on this side. So we say here that our horizontal asymptote is the horizontal line y equals 0. So our vertical asymptote has the equation of a vertical line, which is x equals a number. That's our vertical asymptote. And y equals 0 is the value that our graph approaches as x moves towards positive and negative infinity. So if you wanted to, you could actually use it. You could actually take the x-axis and make it a dotted horizontal line in some way to represent your horizontal asymptote. Okay. So I'm just going to point out here, you can cross. You can cross. It doesn't happen often, but you can cross a horizontal asymptote as opposed to your vertical. All right, so let's take a look at the formal definition now of rational functions, and we'll take a look at 2 parent functions that you'll be able to work with today. So Lucas, since you're here today, I'll give you an opportunity to read number 1. You're welcome. Okay, so if you took a look at this little quotient right here, this ratio, and you covered up the denominator, the top would be a nice polynomial function, and you'd say, oh boy, this is nice. But then you have your denominator, and that's a nice polynomial function, but then you have to worry about your trouble spots. What values of x will make this denominator 0? Because those values will be where you have your, potentially you have your vertical asymptotes, okay? So it looks individually, the numerator and denominator here, this one example I'm giving you, the numerator is a polynomial expression, x squared plus 5x plus 8, it's in polynomial form. The denominator is in factored form. What would be the degree of this polynomial expression in the denominator? What would its degree be? You multiplied it all out. 3, because you've got 3 linear factors. So x, I know. I never doubted it for a moment. Oh yeah, right. I was thinking of you through the whole game. I almost called you. I had a heart attack, you know. All right, so what is the denominator of this, what is the domain of this rational function? So the domain, remember, for polynomial functions is all real numbers. We never have to worry. However, in this particular case, when you're looking at the ratio of 2 polynomials, you can have some trouble spots. So what would be the trouble spots, or what would be the domain for f here? What would the domain look like? Let's put it in set builder notation, since a domain is always a set of numbers. So the domain of f will be all x such that, what can x equal here if we look at that rational function? All right, so we have a -2, because if we put a -2 in here, -2 plus 2 is a 0. If we put x equals 4 in this factor, we get a 0. And of course, when x is all by itself, it could say x take away 0, but we just leave it as x. So the domain of this function is the set of all real numbers except x cannot be -2, 0, or 4. So in set builder notation, that looks like this. And remember, domain is a set. So we always have to have some kind of indication of a set. All right, so let's take a look at two parent functions today, and those will be the basis of all of the rational functions we will graph today. And then on Wednesday, we'll move away from these parent functions into a little more complicated rational functions. So let's take a look at two parent functions. Okay. The two parent functions are going to look like this. This is called the reciprocal function. The reciprocal function. That's how we refer to this. The one other time you've seen the reciprocal function was when we were doing, I think it was in your X class activities when we were doing inverse functions. Because the reciprocal function is one of the functions that has itself for its inverse. So the inverse of f here is 1 over x. So if you take the number 3 and you say 1 divided by 3, you get its reciprocal. If you say 1 divided by 1 over 3, you come right back to 3. So it undoes itself, the reciprocal function. So this is referred to as the reciprocal function. And let's take a look at some of its features. So first we have to think about what number are we going to run into trouble with here? What would be excluded from the domain here? Jessica, can you help me out with this? What couldn't x be here? Is there any value of x that will give us trouble there? Any guesses? No? All right. Helene, how about you? 1. Okay, so if we put 1 in for x, f of 1 would be 1 over 1. Is that a number, 1 over 1? Yeah. Okay, so what was your second idea? 0, because 1 divided by 0, what's that number? It's not defined in our real number system or any system that I know of. So x cannot be 0. So 0 is excluded from this domain. Well, if we were graphing, what does the line, first of all, what does x equals 0 look like on a graph? What does x equals 0 look like? What's our more familiar name for x equals 0? The y-axis, right. So the y-axis is a vertical line. So x equals 0. So this is the y-axis. So x equals 0 is going to be our vertical asymptote. So when I draw a graph of this function, I'm going to take my y-axis and make a dotted line. So what that should start to tell you is some funky things are going to happen as you get really close to 0. Really strange things. So I'm going to just take a blank page here. I don't know what this graph looks like yet. Well, you don't. Some of you don't. So I just put a dotted line to indicate that x equals 0 is my vertical asymptote. And for our conversation today, we're expecting bizarre things to happen when we get close to that line. We're never going to cross it. We're never going to touch it. Okay? And our x-axis, as far as we know, is safe from any problems. Okay? So our y-axis is our vertical asymptote, and our y-axis has the equation x equals 0, because every point that you would plot along that line would have 0 for its x coordinate. All right, let's see where we're going to go from here. So let's fill in these tables together. I'm going to pop out my little wabbit here and use my graphing calculator. Let's clear it. So what we're going to look at is this idea of what happens to the y values, which is the same thing as the value of our function, as x gets really, really close to this excluded value of 0. So we're going to approach it from the right-hand side. Okay, so what that means is, if I come back to this picture, here's 1, and we know the value of our function at 1 is 1. So f of 1 is 1 over 1, which is 1. So here I am, I'm at 1, 1. And now I'm going to start getting closer and closer. Okay, I'm going to take a half. Well, it's the reciprocal function. So what's f of 1/2 going to give me? If it's the reciprocal function, 1 over 1/2, what does that give you? 2. You just take the reciprocal of x. So at a half, you've already jumped up to 2. Here we go. And what if I'm 1/10? What am I? F of 1/10 is 1 divided by 1/10. What does that give me? 10. Right, so now I'm getting really close. There I am at 1/10, and I'm already jumped up to 10. Well, let's take a look at the rest of this. I actually don't need my calculator for this because I know how to, wrong one. I know how to take a reciprocal. So at 1, f of 1 is 1. At a half, f of 1/2 is the reciprocal 2. At 1/10, I'm getting really close to 0 now. I'm only 1/10 of the way to the right. X is 1/10, and I'm already up to 10. What's the next value of x here? How do I read that decimal? 1/100th. So if I take the reciprocal of 1/100th, where am I? 100. Whew. Now I've jumped all the way up the y-axis to 100. And what if I'm really close? I'm at 1,000th to the right. 1,000. So you can see that as I move closer and closer, get closer and closer to that x value being 0, my function is going to just skyrocket up to positive infinity. It's just going to get huge. Sometimes we say it blows up. It grows without bound. Okay. All right. So again, we're examining the behavior near the value of x that makes the denominator 0. We're looking at what happens near the vertical asymptote. So if we look at that direction, we've got to look at it from the left-hand side. So here we are at -1. So what's f of -1? That's like, what's the reciprocal of -1? It's -1. So here we were at 1, 1. Now we're going to be at -1, -1. So notice I've changed the sign of my x value to its opposite, and I notice that my y values are opposite. That is the beginning of an odd symmetry, of a function that has odd symmetry, that has symmetry about the origin. So we'll see as we go along. When we were at 1/2, our value was 2. When we were at 1/10, our value was 10. So if we now notice the pattern that as we change the x value to its opposite, if the y value changes also to its opposite, then we have odd symmetry. So let's keep going here. Let's take a look at this graph. Let's finish this up first. So this idea that we're exploring here, that I've said in language, as the x value approaches 0 from the right, then the value of my function approaches positive infinity. And the way we write that sentence in shorthand notation is, as x approaches 0, and from the right is with this little plus sign. So we're starting out here and we're approaching it from the right-hand side. Sorry, from the right-hand side. All right. Then the value of my function approaches infinity. So you've only been used to looking at x approaches positive and negative infinity with the polynomial function's end behavior. So this is a little different idea. You're actually approaching a single value of x. All right, so if we go the other way, f of -1, so you is -1, f of -1/2. If I take the reciprocal of -1/2, I get -2. So I'm starting to notice that my y values are also opposite when my x values become opposite. F of -1/10 is -10. F of -100 is -100 and -1000. So if we start to plot that out, we go down here to -2 at 1/2, and at 1/10 we're at -10, and then of course at a -100th we're way down here. All right, and so now the graph is approaching this vertical y-axis. It doesn't touch it across it. So as x gets closer and closer to 0, coming in from the left-hand side, what's the value of my function approaching? Closer and closer I get to 0. -infinity, right? So the way we write that is as x gets close to 0 from the left-hand side, the value of my function gets very, 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 very small. It decreases without bound, and we represent that with the symbol -infinity. So in this case, we have a vertical asymptote at the excluded value of 0. Okay, what about the horizontal asymptote? Oh no, horizontal asymptote, what's that mean? Well, before we get there, let's think about x-intercepts and y-intercepts. Is it possible for there to be an x-intercept here? What would an x-intercept look like? Here's our function. What does any x-intercept look like? What would the coordinates be for an x-intercept? Any x-intercept. What would be true about all of them? Y is 0, right? Okay, y is 0, right? And there's some value of x. We don't know what it is. Some little value of x that makes y equal 0. All right, so we look at our reciprocal function, and we're asking, is there a number that when we take its reciprocal, we get 0? There's no number that we take the reciprocal of and get 0, because the only way for a rational function to equal 0 is when you have something up in the numerator other than a constant number. Because the only way for a fraction or a ratio to equal 0 is when you have 0 in the numerator. So as long as you got a constant there, there's never going to be a chance here of this particular function equaling 0. So we have absolutely no x-intercepts. Not possible. Not possible because our numerator is a constant. It's a constant number. It could never equal 0. It equals what it is, which is 1. Okay? So no x-intercepts. All right? What about y-intercepts? Y-intercepts have 0 and some value of y. But what did we just say about the only value this function can't be for x? X cannot be 0. We have that whole dotted line called the y-axis. That's not possible. We can't have either one. Okay? So now we have to look at end behavior. That's the last thing we look at, end behavior. All right? And that means what happens to the value of this function as x grows without bound. So just think about it. If I put in a number like 1 million for x, and I say the value of my function's 1 divided by 1 million, what's that very close to? What value besides Lucas and Haley and Lexi? What's that very close to if you put 1 divided by 1 million in your calculator? 0. Yep. So as x gets really, really big, the value of your function's getting really, really close to the x-axis. It's never going to cross it in this case because we just found out we have no x-intercepts, but it's getting close. And similarly, since this function has odd symmetry, as f approaches, say, negative 1 million, we're going to get 1 over negative 1 million, which approaches 0 as well. So our horizontal asymptote is the line y equals 0, or more familiarly, x-axis. Okay, so I put a red dotted line right down through my y-axis. That's my barrier, my wall. Nothing crosses it or touches it. And I know that as I get, and I just maybe want to plot a few points here just to get me going. And as I approach that line, I get really close to it when I come in from the right, and same thing when I approach it from the left. Okay. And this is the kind of behavior you're always going to see around any vertical asymptotes. Now today we're not going to be working with a bunch of them, but on Wednesday we will be. You have this kind of behavior on either side. When your value is x and you take one teeny step to the right of 0, you're this huge, huge number. If you're on the other side, you go straight down to a very, very small number. So you have this kind of behavior. Notice also you're positive here and you're negative there on either side of that asymptote. And now you do your end behavior. Your end behavior says as this function gets really, really big, this thing is getting really, really close to the horizontal value of y equals 0 for the horizontal axis. So you just do that with some kind of, you show it getting really close. And eventually the width of my pen here is going to look like it's actually on the axis, right? So there is the picture of your parent function 1 over x. Okay? No holes, just these two ideas that are very different. The idea of the vertical asymptote and the idea of your horizontal asymptote. Very different ideas. So today, the symmetry here is odd symmetry, and let's confirm it. Odd symmetry says if you take f of the opposite of x, your y values are opposite. Here's my y value. My y values are opposite. So I know what f of x looks like, so it looks like that, and I put a dash in front. So all I have to do is confirm that when I put the opposite of x into my function, it looks like this. So 1 over the opposite of x is exactly the same as that, because it doesn't matter where that little dash goes, whether it's in the denominator, the numerator, or out front. So this is definitely an odd function. And you notice it has symmetry about the origin. Okay, symmetry about the origin. All right, so the last function we're going to look at today is another parent function which behaves similarly, and we'll go through this more quickly. 1 over x squared. 1 over x squared. Do you expect this to have odd symmetry if you're squaring x? If I put in the opposite of x, do I get the same thing back again? I mean, do I get if I put the opposite of x in, do I get the opposite of what's here? What do I get if I put in the opposite of x here and square it? Same thing. So this is going to have even symmetry. So you're expecting, since f of negative x equals 1 over negative x squared, that equals 1 over x squared, which is f of x. So this has even symmetry. You put an x value in, like 2, you get a quarter. You put in negative 2, you also get a quarter. So this has symmetry about the y-axis. So you're expecting a picture that when you draw one side of it, like the right hand or the left hand side of this graph, you can just fold it over and have the mirror image on the other side of the y-axis. So you only have to do half of the drawing. Okay, so where do we start with rational functions? Always, 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 your first step is to ask, what is the domain? Always ask this question first. What's the domain of my function? So the domain of f is a set of all values of x that define that function. So what does this look like in, say, set builder notation? The set of x such that x cannot equal what number? Johnny? 0. Throw a 0 in there, you're in trouble. So if I were to graph this, I come down here and I, again, right down through x equals 0, which is my y-axis, I put a dotted vertical line. Now, when you do your class activities today, you're going to be very tempted to just look at the answers, not, give your brain a little relaxation and just, look at the answer and copy it. I really encourage you to do your graphs, all your graphs, check with me or a classmate before looking at the answers, because it will just stop you from having to think through the process. Yeah, of course, I can't prevent you from doing that, but I'm just kind of encouraging you to. All right. So here's our domain. So we know we have a vertical asymptote at x equals 0. So the equation, when you're asked on a test or a quiz, your next quiz, what the equation of a vertical asymptote is, every single vertical line has the equation x equals a constant. So in this case, it's x equals 0. So use arrow notation to describe the behavior of our function near the excluded value. So to do that, you have to say, what happens to my function as x approaches 0 from the right and as x approaches 0 from the left? What happens to the value of my function? What does it get close to? So that forces you to think about putting in values of x. So if you're sitting along the x-axis, you start to get values of x that get closer and closer to the y-axis. Okay, closer and closer from both directions. But you only have to do one direction, because once you have the answer for approaching it from either the right or the left, right, you have the exact opposite happen. I mean, the exact same value of y on the other side of the y-axis. So what's happening? In fact, when x is 1 here, when I throw in 1, I get 1 over 1 squared, which is 1. So that's not any different than my reciprocal function. But notice now my values are going to be squared in the denominator, which means they're going to get, when we're approaching it from this side, they're going to get bigger faster, because instead of x being 10 here, to get 1/10, it's going to be 10 squared, which is 100. So when I put 1/10 in here, I'm already way up here at 100th. And then when I put 100th in, I'm all the way up to 1/10,000. So it grows faster than the reciprocal function. You don't even have to go in quite as close to have it really zoom up to infinity. Okay? So the same thing will happen on the other side, because even when I put a negative number in, once I square it, I'm positive. So the same exact thing happens on this side. So as I approach my value of x equals 0 from both sides, from the left and the right, my value of my function, f of x, is getting huge. And similarly, my end behavior is still approaching 0 as x gets really, really big. In fact, it gets closer to 0 much faster. So it doesn't have any x or y intercepts. Nope. And the end behavior says that as x gets really, really big, f of x approaches 0. That's my horizontal asymptotes. As x goes to negative infinity, my function approaches 0. In this case, it can't be 0 because your numerator, look at that numerator, it's 1. So you could never have an x-intercept. Your particular function here will not cross or touch the horizontal. We will see examples on Wednesday where we will cross or touch. Okay. And we already saw that this function has even symmetry, because we can show that f of negative x equals f of x. Since f of x equals 1 over x squared, and I put in negative x and square it, those two things are equal, so I have even symmetry. And that's why once I draw one side of the graph, I just fold it over. I'm all done. So today you're going to be looking at transformations of these two parent functions. So have the image of 1 over x squared in your mind, and have the image of 1 over x in your mind. And then from there, you're either going to be doing some kind of vertical or horizontal stretch or shift or shrink. Okay? You're going to do some type of transformation to these graphs. So you have quite a few exercises to do here, or 3 of them, and then you can go back and finish whatever you did not finish from class 28 and 29, and ask questions, because class 28 and 29 is on your quiz today, so that will be good to check in with me about.